Hello there, and welcome to Space Historians. I'm truly glad you've joined me tonight, ready to slow down, breathe deeply, and let your thoughts drift weightlessly beyond the edges of everything familiar. Tonight, we're not rushing through facts or racing toward conclusions. We're gliding gently through one of humanity's most profound questions, one that sounds simple but opens into something vast. How far can we actually travel in space right now? Not in dreams or science fiction, but in reality, with the machines and materials that exist today, at this very moment. Before we begin, I'd love to know, where in the world are you listening from? And what time is it where you are? It always amazes me how the same stars shine above all of us, how the same darkness wraps around the planet no matter where you rest your head tonight. If you enjoy these quiet journeys through the cosmos, a like and a subscribe help keep this channel drifting steadily through the infinite. And for those who've already joined this growing constellation of listeners, thank you. You are part of this voyage, part of this shared wonder. Each episode here isn't just about numbers or distances. It's about the stories behind them, the people who dared to reach farther, the machines still travelling in silence billions of kilometres from home, and the quiet realisation that we, right now, are living in the age when humanity first learned to leave its cradle. So tonight, as your breathing slows and your eyes grow heavy, imagine yourself floating gently upward. The ground falls away, the blue sky fades to black, and there, stretching out in every direction, is the question we're here to explore together. How far have we gone? How far can we go? And what does distance really mean when you're surrounded by infinity? If you gently press the notification bell, you'll always know when the next journey begins. But for now, you don't need to do anything but listen, breathe, and drift. Let's travel together, not through space, but through understanding. Welcome to the quiet side of the cosmos. There is something impossible about the fact that you are here, right now, listening to these words on a planet that is hurtling through space at nearly 30 kilometers every single second. You don't feel it. The air around you is still. The walls are steady. But beneath the surface of your everyday experience, you are moving faster than any bullet, faster than sound, faster than the fastest aircraft ever built, and you've been doing it your entire life without noticing. Earth spins. It orbits. It drifts through the galaxy. And somewhere out there, beyond the thin layer of air that keeps you breathing, humans have learned to leave. We've built machines that can slip free of gravity's grip. We've sent people into the void and brought them back alive. We've walked on another world, left footprints in dust that hasn't been disturbed by wind in billions of years. And we've launched spacecraft that are still travelling. Right now. This very second. Racing away from the sun at speeds so high they'll never stop, never turn around, never come home. That sounds like science fiction, but it's not. It's just science. It's the world you live in. The question tonight is deceptively simple. How far can we travel in space right now? Not someday. Not in theory. But today, with the technology we have, the rockets we've built, the fuel we can carry, the bodies we're born with, the answer is both smaller and larger than you might think. Let's start with something you probably know but may never have truly considered. Right now, at this very moment, there are people floating above your head, not metaphorically, literally. Human beings, alive and breathing, orbiting the Earth at about 28,000 kilometers per hour, circling the entire planet every 90 minutes. They live on the International Space Station, a structure about the size of a football field, assembled piece by piece over decades. It floats roughly 400 kilometers above the surface. That sounds far, but in the scale of space, it's barely a whisper away from home. If Earth were the size of an apple, the station would hover less than a millimeter above the skin. That's the first measure of how far we can go. We can live and work just beyond the atmosphere, but only by clinging tightly to the planet. Now stretch your imagination a little farther. The farthest any human being has ever travelled from Earth is the Moon. Between 1968 and 1972, 24 astronauts made the journey. 12 of them walked on its surface. The rest stayed in orbit, circling alone while their crewmates descended. The Moon sits, on average, about 384,000 kilometers away. That's roughly 30 times the diameter of Earth itself. The trip took about 3 days each way. 3 days to cross a gap that had existed for billions of years, untouched, unwatched, silent. And here's the astonishing part. It's been more than 50 years since the last person stood there. More than 50 years since anyone travelled farther than low Earth orbit. The Moon remains the absolute edge of human exploration. No one has gone beyond. Not because we forgot how, but because the challenge of going farther is so immense that we're still building the tools to try. But we've sent machines much, much farther. Right now, there are 5 spacecraft that have escaped the Sun's gravitational pull entirely. Voyager 1, Voyager 2, Pioneer 10, Pioneer 11, and New Horizons. They're all still moving, coasting through the space between stars, powered by nothing but momentum and the faint warmth of decaying plutonium. Voyager 1, launched in 1977, is the most distant human-made object in existence. It's over 24 billion kilometers from Earth. That number is so large it stops meaning anything. Let me put it another way. The light from Voyager's transmitter, travelling at the fastest speed possible in the universe, takes more than 22 hours to reach us. Every signal is a message from yesterday. At the speed Voyager is travelling, it would take 70,000 years to reach the nearest star beyond our Sun. 70,000 years! That's longer than all of recorded human history. Longer than agriculture, longer than language as we know it. And yet, in the scale of the galaxy, Voyager has barely left the neighbourhood. It's still within the Sun's influence. Still in what we call the solar system. The stars you see at night, the ones that look so close you feel like you could reach out and touch them, are trillions upon trillions of kilometers away. Distances so vast that even light, which crosses the space between Earth and the Moon in just over a second, takes years to make the journey. So here's the edge of everything. We can send people to the Moon and back. We can keep them alive in orbit for months at a time. We can send machines to every planet in the solar system and even beyond, into the space between the stars. But the stars themselves? They remain, for now, completely beyond our reach. That's not a failure, it's a fact. A humbling, awe-inspiring fact about the scale of the universe and the fragility of the tiny biological machines we call human bodies. The question isn't whether we'll ever go farther. The question is how. And that's where the story really begins. Every journey into space begins the same way. With weight. You feel it right now, pressing you gently into whatever surface supports you. It's so constant, so familiar, that you barely notice it. But gravity is the reason space travel is hard. It's the invisible hand that holds you to the ground, that keeps the air around you from drifting away, that makes water flow downhill and birds work so hard to stay aloft. Gravity is both your protector and your prison. To understand how far we can travel in space, you first have to understand how difficult it is to leave in the first place. Earth's gravity doesn't just fade away a few kilometers up. It extends outward for thousands of kilometers, pulling on everything, even the moon itself. The International Space Station, floating 400 kilometers above the surface, still experiences about 90% of Earth's gravitational pull. It doesn't float because there's no gravity up there. It floats because it's moving sideways so fast that it keeps falling around the planet instead of into it. That's what orbit is, controlled falling, a delicate balance between velocity and gravity that keeps you perpetually on the edge of coming home. To reach orbit, you need speed, enormous speed, about 28,000 kilometers per hour, or roughly 8 kilometers every single second. That's faster than most people will ever travel in their entire lives, and it's just the minimum requirement to stay above the atmosphere without crashing back down. But orbit isn't escape, it's just the first step. To actually leave Earth, to travel to the Moon or Mars or anywhere beyond, you need even more speed. The escape velocity from Earth's surface is about 40,000 kilometers per hour. That's the speed at which gravity finally loses its grip. The threshold where motion becomes freedom. Reaching that speed requires fuel, massive amounts of it. And here's the problem. Fuel has weight, and weight requires more fuel to lift, which adds more weight, which requires even more fuel. It's a loop. A mathematical trap called the tyranny of the rocket equation, and it's the reason most of a rocket is just fuel. When the Saturn V launched toward the Moon, it weighed nearly 3,000 tons at liftoff. The command module that actually went to the Moon and back weighed less than 6 tons. Everything else, more than 99% of the total mass, was fuel, engines, and stages that burned up or fell away during ascent. All that effort, all that energy, just to push a tiny capsule fast enough to break free. And even then, the astronauts didn't go straight to the Moon. They orbited Earth first, checked their systems, then fired their engine one more time to push themselves onto a trajectory that would carry them across the void. It took 3 days to cross the gap, coasting most of the way, falling toward the Moon's gravity just as they'd been falling toward Earth's before. That's the physical reality of leaving home. It's not like getting on a plane. It's not even like climbing a mountain. It's a fight against one of the fundamental forces of the universe, one that never stops pulling, never gives up, never lets you forget where you came from. But here's the beautiful part. We learned how to win that fight. It started in 1957 when the Soviet Union launched Sputnik, the first artificial satellite. It was a metal sphere about the size of a beach ball with 4 long antennas and a radio transmitter that sent out a simple beeping signal. That beep, travelling down from orbit, was humanity's first voice from beyond the atmosphere. It proved that leaving was possible. 4 years later, Yuri Gagarin became the first human to reach space. His spacecraft, Vostok 1, made a single orbit around the Earth before returning safely. The entire flight lasted less than 2 hours, but in that time, Gagarin saw something no human had ever seen before. The curve of the planet, the thinness of the atmosphere, the blackness beyond. He said, looking at Earth from space, that it was remarkably beautiful, but also surprisingly small. That perspective, that shift in understanding, became known as the overview effect. Almost every astronaut who's been to space describes it. The sudden, overwhelming realization that Earth is a fragile, isolated island in an ocean of emptiness. That the borders we draw, the conflicts we wage, the divisions we maintain, all of it looks absurd when seen from above. From orbit, there are no countries, just one world, spinning quietly in the dark. But orbit, as transformative as it is still just the beginning. The Kármán line, the boundary where space officially begins, sits about 100 kilometers above sea level. It's not a wall or a physical barrier. It's just the altitude where the atmosphere becomes too thin for aircraft to generate lift. Above that line, wings don't work. You need rockets. You need thrust. You need to push against nothing but your own momentum. And once you're past that line, the rules change. There's no air to breathe, no pressure to hold your blood in place, no protection from radiation. The temperature swings wildly. In sunlight, surfaces can heat to over 100 degrees. In shadow, they plunge to nearly 200 below zero. Your body, built for Earth's environment, becomes a fragile biological system that needs constant support just to survive. That's why the space station exists. It's not just a laboratory or an outpost. It's a lesson in humility. A reminder that even 400 kilometers from home, even in the place humans have visited most often beyond Earth's surface, survival is still a carefully managed act of engineering and willpower. The astronauts up there right now breathe recycled air. They drink recycled water. They eat food shipped up from the surface at enormous cost. They exercise for hours every day just to keep their bones from weakening in the absence of gravity. And they know, every single moment, that they're alive only because of the thin metal shell around them and the systems that keep it pressurized, heated, and shielded from the void. That shell, that dependence, that fragility, it defines the outer limit of where we can live. We can visit space. We can work there. But we can't truly live there. Not the way we live on Earth. Not yet. So the question of how far we can travel isn't just about speed or fuel. It's about life. About keeping a heartbeat steady and a mind clear across distances that were never meant for creatures like us. And that's where the real challenge begins. There was a time, not very long ago, when the idea of leaving Earth was pure fantasy. For most of human history, space was unreachable. Not just difficult, not just dangerous, completely, fundamentally impossible. The sky was a ceiling made of something invisible but absolute. Birds could touch it, clouds could drift through it, but humans? We were bound to the ground by forces we didn't understand and couldn't overcome. Then, slowly, something changed. Not all at once, not with a single breakthrough. But piece by piece, over centuries, we began to understand the rules. Isaac Newton, in the 1600s, figured out that the same force pulling an apple to the ground was also holding the moon in orbit. Gravity wasn't just something that kept us down. It was a universal principle, one that governed everything from falling leaves to spinning galaxies. And if you understood it, you could work with it, maybe even against it. Konstantin Tsiolkovsky, a Russian schoolteacher in the late 1800s, started thinking about rockets. Not the fireworks kind, but engines capable of reaching space. He worked out the mathematics, the brutal truth of how much fuel you'd need, how fast you'd have to go, how the mass of your vehicle would fight you every step of the way. He realized that multi-stage rockets, engines that dropped away as their fuel ran out, were the only practical way to reach orbit. And he was right. But knowing how to do something and actually doing it are very different things. The real breakthrough came after World War II, when both the United States and the Soviet Union began building rockets based on German wartime designs. These weren't for exploration. They were weapons, missiles designed to carry explosives across continents. But the same technology that could deliver destruction could, theoretically, carry something else, something peaceful, something alive. In 1957, the Soviet Union launched Sputnik. It wasn't a weapon. It wasn't even particularly useful. It was a metal ball with a radio inside, launched into orbit just to prove it could be done. And that simple act, that beeping signal crossing the sky every 90 minutes, changed everything. Because if you could put a satellite in orbit, you could put anything in orbit, including a person. The race was on. 4 years later, on the 12th of April, 1961, Yuri Gagarin strapped himself into a spacecraft called Vostok 1. It was small, cramped, barely big enough for him to sit. He had almost no control over it. The flight path was automatic. If something went wrong, there was no backup plan, no way to abort, no guarantee he'd survive re-entry. But he went anyway. The rocket lifted off from a remote launch site in Kazakhstan. The engines roared. The ground fell away. And for the first time in the history of life on Earth, a human being left the atmosphere. Gagarin's flight lasted 1 hour and 48 minutes. A single orbit, one trip around the planet. He saw the curvature of the Earth, the blackness of space, the stars unblinking in the void. He experienced weightlessness, that strange sensation of falling forever without hitting the ground. And then, after less than 2 hours, he came back. He landed in a field, parachuting down separately from his capsule, and when local farmers found him, still in his orange flight suit, they weren't sure what to make of him. He smiled and told them he'd just come from space. And it was true. That moment, that flight, that impossible accomplishment, it wasn't just a technological achievement. It was a spark, a realization. The sky wasn't a ceiling after all. It was a doorway. And we'd just learned how to open it. Less than a month later, Alan Shepard became the first American in space. His flight was even shorter, just 15 minutes, a suborbital arc that barely kissed the edge of the atmosphere before falling back. But it was proof that the United States could do it too, that the door was open for everyone. And then, in 1962, John Glenn became the first American to orbit the Earth. 3 times around, nearly 5 hours in space, long enough to see multiple sunrises, to feel the strange rhythm of orbiting, to understand that this wasn't just a stunt. This was real. This was sustainable. This was the beginning of something larger. The discovery wasn't just that we could leave. It was that we could come back. That space wasn't a one-way trip into the unknown. It was a place we could visit, explore, and return from. A place where humans could survive, at least for a little while. But there was something else, something quieter, but just as profound. Every astronaut who went to space came back, changed. Not physically, though some experienced nausea, disorientation, muscle loss. But mentally, emotionally, they saw Earth from a perspective no human had ever had before, and it shifted something deep inside them. They saw how thin the atmosphere was, how fragile the line between life and emptiness. They saw the planet as a whole, borderless and singular, a blue marble floating in an infinite black ocean. They saw home the way you might see it if you'd been away for years. Suddenly precious, suddenly small, suddenly worth protecting. That perspective, that shift, became part of the reason we go to space. Not just to explore, not just to prove we can, but to see ourselves more clearly, to understand what we're part of, to recognize that the ground beneath us, the air around us, the warmth of the sun, all of it is rare and delicate and worth caring for. The discovery of space travel wasn't just about technology, it was about awareness, about realizing that the universe is vast, but also that we're part of it, that we're not separate from the stars, we're made of the same materials, we're governed by the same laws. And now, for the first time, we could go out there and see it for ourselves. The question stopped being whether we could leave. The question became how far we could go. And that question, that spark of curiosity, has been burning ever since. It's the reason we kept building bigger rockets. The reason we dreamed of the moon. The reason we're still reaching, still pushing, still wondering what's out there waiting for us. Because once you know the door is open, it's very hard to stop walking through it. When the first astronauts returned from space and tried to describe what they'd seen, they struggled, not because they lacked the words, but because the experience was so far removed from anything humans had ever felt before that language itself seemed inadequate. How do you explain the colour of Earth from orbit? The way the atmosphere looks like a thin blue line, impossibly delicate, impossibly fragile? How do you describe the silence, the vastness, the sudden overwhelming awareness that you're floating in nothing, held in place only by velocity and mathematics? Some said it was beautiful. Some said it was terrifying. Most said it was both. Frank Borman, commander of Apollo 8, the first mission to orbit the moon, looked back at Earth from nearly 400,000 kilometers away and said it was the most beautiful thing he'd ever seen. A tiny, perfect sphere glowing softly against the blackness. No borders visible, no conflicts, just one world, whole and singular. Jim Lovell, on the same mission, held up his thumb and realized he could block out the entire planet. Everything he'd ever known, everyone he'd ever loved, every mountain, ocean, city, and star-filled night, all of it hidden behind the width of his thumb. That moment, that realization, became one of the defining images of space exploration. Not a photograph, not a measurement, just a simple gesture that showed how small we are, how far we'd come, and how much we'd left behind. But not everyone responded with awe. Some people didn't believe in it at all. When the first grainy images of Earth from space were broadcast on television, when astronauts described the curvature of the horizon and the blackness beyond, there were those who insisted it was fake, that the whole thing was staged, filmed in a warehouse somewhere, designed to win a political race rather than a scientific one. Conspiracy theories sprouted almost immediately, fed by mistrust, by Cold War paranoia, by the simple human tendency to reject what seems impossible. And in a way, it's understandable. For thousands of years, space was unreachable. For nearly all of human history, the idea of leaving Earth was pure fantasy, something reserved for myths and dreams. To suddenly be told that humans had not only reached space but were casually orbiting the planet, reusable spacecraft carrying crews up and down like a shuttle bus. That was a lot to accept, especially when most people would never experience it themselves. But for those who did go, the experience was undeniable, and it changed them. Buzz Aldrin, the second person to walk on the moon, later described a period of deep depression after returning. Not because the mission had failed, but because nothing on Earth could ever match the intensity of what he'd experienced. He'd stood on another world, looked up at a black sky in the middle of the day, and seen Earth hanging above him like a fragile ornament. And then he came back, and life went on as if nothing had happened. That disconnect, That gap between the profound and the mundane affected many astronauts. Some struggled to readjust. Some became advocates for space exploration, spending the rest of their lives trying to share what they'd learned. Others withdrew, carrying the experience quietly inside them, unable or unwilling to put it into words. Edgar Mitchell, who walked on the moon during Apollo 14, said the experience gave him a profound sense of interconnectedness. That seeing Earth from space made him realize that everything, everyone, all of it, was part of a single living system. He spent the rest of his life studying consciousness, trying to understand the deeper implications of what he'd felt out there. Michael Collins, who stayed in orbit while his crewmates walked on the moon, described a strange kind of solitude. For 48 minutes of every orbit, he was completely alone, cut off from both Earth and the lunar surface, farther from other human beings than anyone had ever been. He said it wasn't lonely, it was peaceful, a rare, absolute silence that let him think more clearly than he ever had before. These weren't just reactions to a new place, they were responses to a new perspective. Space didn't just show astronauts the universe, it showed them themselves. It gave them a vantage point from which to see their own species, their own planet, their own existence, in a way that no one in history had ever seen it before. And that perspective, that shift in awareness, began to spread. The photographs taken during the Apollo missions, especially the one known as Earthrise, the image of Earth rising above the lunar horizon, became some of the most influential images ever created. Not because they were technically perfect, but because they showed something people had never truly understood before. The Earth wasn't just our home, it was our only home. A tiny island of life in an ocean of emptiness, beautiful and fragile and desperately worth protecting. Environmental movements gained momentum after those images were released. People who saw Earth from space, even through a photograph, began to think differently about borders, about resources, about the long-term survival of the species. The phrase "spaceship Earth" became popular, the idea that we're all passengers on the same vessel, travelling through space together, dependent on the same limited systems to keep us alive. That's the power of perspective. It doesn't just change what you know, it changes what you value, what you care about, what you're willing to fight for. And yet, for all the awe and transformation, there was also a quiet sadness, because the more people saw of space, the more they realized how far we still had to go. The moon was an achievement, yes, but it was also a reminder of how much farther everything else was. Mars, the outer planets, the stars, all of it remained out of reach, separated from us not just by distance but by time, by biology, by the fundamental limits of what our bodies and our machines could endure. The response to space wasn't just wonder, it was also a kind of grief. The grief of realizing how small we are, how brief our lives, how limited our reach. The grief of knowing that the universe is vast and beautiful and mostly, for now, beyond us. But grief, when mixed with awe, becomes something else. It becomes reverence, respect, a determination to keep trying, even if the goal seems impossible. Because once you've seen the Earth from space, once you've looked back at the blue marble and understood what it means, you can't unsee it. You can't stop caring. You can't stop reaching. That's what the first astronauts brought back. Not moon rocks or data, but a new way of seeing, a new kind of awareness. And that, more than anything, is why we keep going. There's a strange tension at the heart of space exploration. On one side, pure mathematics, the cold, predictable laws of physics that govern velocity, mass, trajectory. On the other side, the wild, irrational pull of human curiosity, the desire to reach farther even when the numbers say it's impossible. Science tells us exactly how far we can go, but something deeper tells us we should try to go farther anyway. The problem begins with the rocket equation, a formula worked out more than 100 years ago that describes the fundamental challenge of space travel. To go faster, you need more fuel. But fuel has mass, and mass requires more fuel to lift, which adds more mass, which requires even more fuel. It's a loop, a trap, a ceiling that gets harder to break through with every additional kilometer per second you want to achieve. Konstantin Tsiolkovsky, the Russian scientist who first formalized the equation, understood this. He knew that chemical rockets, the kind that burn fuel to produce thrust, would only ever take us so far. They're limited by the energy density of the fuel itself. You can only pack so much power into a kilogram of matter before it stops being practical to carry. That limit defines our current reach. The rockets we use today, descendants of designs from the 1960s and 70s, are extraordinarily efficient by historical standards. But they're still chemical. They still burn hydrogen, kerosene, or solid propellants. And they still face the same fundamental problem that Tsiolkovsky identified more than a century ago. To reach low Earth orbit requires a rocket that's mostly fuel. To reach the Moon requires even more. To reach Mars, even more still. And to reach another star, with chemical rockets, it's not just impractical, it's impossible. The amount of fuel you'd need to accelerate a spacecraft to even a fraction of light speed is larger than the mass of planets. It simply can't be done. So the question becomes, if chemical rockets can't take us to the stars, what can? This is where the conflict emerges. The tension between what we know and what we hope. The gap between current technology and human ambition. Nuclear propulsion is one answer. Instead of burning fuel, you use the heat from a nuclear reactor to superheat a propellant and shoot it out the back of your spacecraft. It's far more efficient than chemical rockets, capable of much higher exhaust velocities, which means you need less mass to achieve the same speed. NASA studied nuclear thermal rockets extensively in the 1960s and 70s. They even built and tested prototypes, but the program was cancelled, partly due to cost, partly due to safety concerns, partly because the political will to push forward simply faded after the Apollo era ended. Ion drives are another possibility. These engines use electricity to accelerate ions, tiny charged particles, to extremely high speeds. The thrust is incredibly low, barely enough to lift a piece of paper on Earth's surface, but in the vacuum of space, where there's no friction, that tiny constant push can build up over time, eventually reaching speeds far higher than any chemical rocket could achieve. NASA's Dawn spacecraft used ion propulsion to visit the asteroid Vesta and the dwarf planet Ceres, becoming the first mission to orbit 2 extraterrestrial bodies. It worked, but it was slow, the kind of slow that makes patience feel like the primary requirement for interplanetary travel. And then there's fusion. Theoretical engines that would harness the same process that powers the stars, fusing light elements like hydrogen into heavier ones and releasing enormous amounts of energy in the process. If we could build a working fusion drive, we could theoretically reach a significant fraction of light speed, enough to make trips to nearby stars feasible within a human lifetime. But fusion remains stubbornly out of reach. We've been trying to build practical fusion reactors for decades, and we're still not there. The technology exists in theory, but theory and engineering are separated by an ocean of practical problems that no one has solved yet. That's the scientific side of the conflict. We know what would work, we just don't know how to build it. But there's another side, a stranger one, that doesn't rely on engineering at all. It's the side that asks, what if we're thinking about distance wrong? What if space travel isn't just about propulsion and fuel, but about something deeper? This is where science meets mystery, where physics brushes up against philosophy and speculation. Some physicists have proposed that space-time itself might be malleable, that if you could bend or warp it, you could theoretically travel faster than light without actually accelerating to light speed. The Alcubierre drive, named after physicist Miguel Alcubierre, describes a theoretical method of contracting space in front of a spacecraft and expanding it behind, creating a bubble that moves through space faster than light, while the ship inside remains stationary relative to the bubble itself. It doesn't violate relativity, it exploits it. The catch? You'd need exotic matter, material with negative mass, something that's never been observed and may not even exist. And the energy requirements are staggering, possibly greater than the total mass energy of the observable universe. It's mathematically possible but practically impossible, at least for now. Then there's the idea of wormholes, theoretical shortcuts through space-time that could connect distant parts of the universe. If they exist, and if they could be stabilized, and if a spacecraft could survive the journey through one, you could theoretically travel light years in an instant. But again, the problems are immense. Wormholes, if they exist, are probably microscopic and incredibly unstable. Making one large enough and stable enough for a spacecraft would require technology so far beyond what we currently have that it's almost pointless to speculate about. These ideas exist in the liminal space between science and dreams. They're rooted in real mathematics, but they depend on materials and energy sources we don't have access to. They're not impossible, exactly, but they're so far beyond our current capabilities that they might as well be. And that's the conflict. We're caught between what we can do and what we want to do. Between the slow, steady progress of engineering and the wild, impatient pull of imagination, between rockets that barely get us to the moon and theories that promise the stars. It's frustrating and it's humbling, because it means that right now, at this exact moment in history, the farthest we can realistically travel is still within our own solar system. Mars is achievable, maybe the moons of Jupiter or Saturn, if we're willing to wait years for a spacecraft to get there. But the stars? They remain, for now, completely out of reach. That doesn't mean we stop trying. It doesn't mean we give up on fusion, on nuclear propulsion, on ion drives, on any of the technologies that might one day take us farther. But it does mean we have to be honest about where we are. And where we are is still very, very close to home. The conflict isn't resolved, it's ongoing. Every generation of scientists and engineers pushes a little farther, learns a little more, builds a little better. But the gap between current reality and distant possibility remains vast. And maybe that's okay. Maybe the tension is part of the process. Maybe the conflict is what keeps us moving forward. Understanding how far we can travel means understanding what we've already done, not in theory, not in speculation, but in actual, verifiable missions that launched, travelled, and succeeded. Let's start with orbit. The closest destination, the easiest to reach, and the place humans visit most often. The International Space Station orbits at an altitude of about 408 kilometers. It's been continuously inhabited since the year 2000, making it one of the longest-running experiments in human endurance outside Earth's atmosphere. Astronauts typically stay for 6 months, though some have remained for nearly a year. The station itself is a collaboration between multiple countries, assembled piece by piece over more than a decade, and it serves as a laboratory, a testbed for long-duration spaceflight, and a symbol of what humanity can achieve when we work together. But the station isn't free-floating. It's constantly falling back toward Earth, pulled down by gravity and slowed by the thin traces of atmosphere that still exist at that altitude. Every few weeks, it has to fire its engines to boost itself back up, to maintain its orbit. Without those corrections, it would spiral down and burn up in the atmosphere within months. That's the first clue about distance in space. Even 400 kilometers up, you're not truly free of Earth. You're just moving fast enough to stay ahead of the fall. Beyond the station, humans have traveled to the Moon. 6 Apollo missions successfully landed between 1969 and 1972. Each trip took 3 days outbound, 3 days back. The astronauts used a combination of Earth orbit, translunar injection burns, and lunar orbit insertion to navigate the gap. They didn't fly in a straight line. They followed curved trajectories, falling toward the Moon's gravity, while Earth's gravity slowly released its grip. The farthest any human has travelled from Earth was during Apollo 13, the mission that famously survived a catastrophic explosion on the way to the Moon. After the oxygen tank ruptured, the crew had to loop around the far side of the Moon and use its gravity to slingshot back toward Earth. At their most distant point, they were 400,000 kilometers from home, farther than anyone before or since. And that's it. That's the limit of human space travel. 400,000 kilometers. Less than the distance light travels in 1.5 seconds. But machines have gone much, much farther. The Voyager spacecraft, launched in 1977, are the most distant human-made objects in existence. Voyager 1 is currently more than 24 billion kilometers from Earth, traveling at roughly 61,000 kilometers per hour. It crossed into interstellar space in 2012, passing beyond the heliopause, the boundary where the sun's influence fades and the space between stars begins. But here's the thing. Even at that distance, even after more than 47 years of travel, Voyager 1 is still within the Sun's gravitational well. It's still, technically, part of the solar system. The Oort cloud, a vast sphere of icy objects that surrounds the Sun, extends outward for nearly 2 light-years. Voyager won't reach the inner edge of it for another 300 years. And it won't leave it entirely for 30,000 years. That gives you a sense of scale. The solar system is far larger than most people realize, and even our fastest spacecraft are barely crawling through it. The journey to Mars, the next logical destination for human exploration, takes about 7 months using current propulsion technology. The distance varies depending on where Earth and Mars are in their orbits. At closest approach, Mars is about 55 million kilometers away. At its farthest, more than 400 million. Launch windows, the times when the planets are favourably aligned, occur roughly every 26 months. NASA has sent multiple rovers to Mars: Spirit, Opportunity, Curiosity, and Perseverance. All of them landed successfully, though Spirit and Opportunity have since stopped functioning. Perseverance, the most recent arrival, touched down in 2021 and is still operating. It carries a small helicopter, Ingenuity, that has completed dozens of flights, proving that powered flight is possible in the thin Martian atmosphere. These missions provide clues about what human travel to Mars would require. The spacecraft need heat shields to survive re-entry. They need parachutes and retro-rockets to slow down. They need power sources that can function for years without maintenance, and they need to withstand radiation, temperature extremes, and the long, lonely silence of deep space. Farther out, we've sent probes to every planet in the solar system. Pioneer 10 and 11 flew by Jupiter and Saturn. Voyager 1 and 2 visited Jupiter, Saturn, Uranus, and Neptune. Cassini orbited Saturn for 13 years, studying its rings and moons in extraordinary detail. New Horizons flew by Pluto in 2015, giving us our first close-up images of the distant dwarf planet. Each of these missions required years of travel. Cassini took 7 years to reach Saturn. New Horizons took 9.5 to reach Pluto, and both used gravity assists, swinging by other planets to pick up speed, because no rocket we've built can carry enough fuel to make the journey on its own power alone. The clues are clear. Distance in space isn't just measured in kilometers. It's measured in time, in years, in the slow, patient drift of spacecraft across the void. And there's another clue, one that's easy to overlook. None of these missions were crewed. None of them carried life support systems, food, water, or air recycling. They didn't need to keep anyone alive. They just needed to function long enough to complete their objectives and send back data. Keeping humans alive for the same durations would be exponentially harder. You'd need radiation shielding, far more robust than what's currently available. You'd need artificial gravity, or at least a way to mitigate the bone and muscle loss that comes from extended weightlessness. You'd need psychological support, ways to keep the crew sane during months or years of isolation, and you'd need a way to bring them home. That's the real investigation. The pursuit isn't just about reaching a destination, it's about surviving the journey. About designing systems that can function in environments where failure means death. About calculating risks and building redundancies and accepting that some things, no matter how carefully planned, might still go wrong. The evidence tells us that machines can travel throughout the solar system, that humans can survive in space, but only with enormous support, that the moon is reachable in days, that Mars would take months, that the outer planets would take years, and that anything beyond, the stars themselves, would take lifetimes. These aren't guesses, they're measurements, verified, repeatable, tested across decades of missions. The investigation into how far we can travel isn't a mystery anymore. It's a map, one that shows exactly where we've been, where we can go, and how impossibly far away everything else remains. There's a moment in every exploration story when you realize the real challenge isn't what you thought it was. For space travel, that moment comes when you understand that distance is only part of the problem. The deeper mystery, the one that defines how far we can actually go, isn't just about propulsion or fuel or speed. It's about time. Time changes everything in space, not in the poetic sense, in the literal, physical sense. The farther you go, the longer it takes. And the longer it takes, the more problems emerge. Problems that have nothing to do with engines or trajectories. Let's start with radiation. Earth's atmosphere and magnetic field shield us from most of the radiation that floods through the solar system. Cosmic rays, high-energy particles from exploding stars, solar wind, streams of charged particles from the sun, all of it deflected, absorbed or scattered before it reaches the surface. We live in a bubble of protection so effective that most people never even think about it. But in space, that protection is gone. The International Space Station orbits within Earth's magnetic field, so astronauts there are partially shielded. But beyond that? Beyond low Earth orbit, There's nothing between you and the radiation except the walls of your spacecraft, and those walls aren't enough. Aluminum, the material most spacecraft are made from, does block some radiation, but not all of it. High-energy particles can pass right through, and when they do, they damage cells. They increase the risk of cancer. They affect the brain, causing cognitive impairments that some astronauts have described as mental fog, difficulty concentrating, memory problems. A trip to Mars, 7 months each way, would expose astronauts to radiation levels far beyond what's considered safe. We don't have a good solution yet. Water can act as shielding, so can certain plastics. But both are heavy, and weight is always the enemy in space travel. The more shielding you carry, the more fuel you need, the more expensive and complicated the mission becomes. That's the first part of the deeper mystery. Radiation isn't a problem you can solve with better engines. It's a problem of exposure over time. Then there's the psychological challenge. Isolation. The longest anyone has spent in space continuously is 437 days, set by Russian cosmonaut Valery Polyakov aboard the Mir space station in the mid-90s. He stayed sane. He completed his mission, but he also had regular communication with Earth, supply missions every few months, and the knowledge that he could come home if something went wrong. A trip to Mars wouldn't have those comforts. Communication would be delayed by anywhere from 3 to 22 minutes, depending on how far apart the planets were at the time. You couldn't have a conversation. You could only send messages and wait for replies. If something broke, if someone got sick, if psychological stress became unbearable, there would be no quick rescue, no early return option. You'd be committed, locked into a journey lasting years, surrounded by the same few people, in a space the size of a small house, with nothing outside but emptiness. Some research has been done on isolation. Crews have lived in simulated Mars habitats on Earth for months at a time, testing how they handle confinement, boredom, interpersonal conflict. The results are mixed. Some crews do fine, others struggle. Personality clashes emerge, motivation fades. The sameness of each day, the lack of variety, the inability to step outside and feel wind or rain or sunlight, it wears people down in ways that are hard to predict. That's the second part of the mystery. The farther you go, the more psychological endurance matters, and we're still learning how to select for that, how to train for it, how to support it. Then there's biology itself. Human bodies are built for Earth, for gravity, for a 24-hour day, for an atmosphere with a specific mix of gases. Take any of that away, and problems start to appear. In microgravity, bones lose density, muscles atrophy. Fluids shift upward, causing facial puffiness and increased pressure in the skull. The heart, no longer working against gravity, becomes weaker. The immune system becomes less effective. Vision changes occur, possibly due to pressure on the optic nerve. Some of these effects are reversible after returning to Earth. Others might not be. And Mars, though it has gravity, only has about 38% of Earth's. No one knows what long-term exposure to that would do. Would it be enough to prevent bone loss? Or would it just slow the decline without stopping it? Would children born on Mars develop normally? Or would their bodies, shaped by lower gravity, be unable to adapt to Earth if they ever wanted to return? These aren't hypothetical questions. They're the real barriers to long-term space settlement. And we don't have answers yet. That's the turning point. The moment when you realize that the question of how far we can travel isn't just about distance. It's about how much time our bodies and minds can endure in an environment they weren't designed for. You can build faster rockets. You can improve fuel efficiency. You can map trajectories with perfect precision, but you can't change the fact that humans are fragile, that we evolved for a specific planet, a specific set of conditions, and that leaving those conditions behind comes with costs we're still trying to understand. The deeper mystery is this. Maybe the limit isn't out there. Maybe it's in here, in our biology, in our psychology, in the fact that we're creatures of Earth, trying to become creatures of space, and the transformation is harder than we expected. That doesn't mean it's impossible. It just means the challenge is different than we thought. It's not just engineering, it's medicine, it's psychology, it's biology. It's all of it, working together, trying to solve the problem of how to keep a human alive, sane, and healthy for the months or years it would take to reach the farther parts of our solar system. And that realization changes everything. Because it means the answer to how far we can travel might depend less on the machines we build, and more on how well we understand ourselves. Every journey into space changes something, not just for the people who go, but for everyone who watches, everyone who learns, everyone who begins to see the world differently because of what was discovered. The impacts don't always arrive immediately. Sometimes they take years to reveal themselves. Sometimes they're invisible until you look back and realize how much has shifted. When the first astronauts returned from space, they brought back more than photographs and moon rocks. They brought back perspective, a new way of seeing Earth that began to ripple outward through culture, politics, science, and art. The environmental movement gained momentum in the years following the Apollo missions. Not coincidentally, the images of Earth from space, especially the iconic Earthrise photograph taken during Apollo 8, showed people something they'd never fully grasped before. The planet was finite, fragile, isolated in the vast darkness. There was no backup, no spare world waiting if we damaged this one. That realization, quiet but profound, helped shift how people thought about pollution, resource use, conservation. It's hard to ignore the fact that the air, the water, the land, all of it is limited when you can see the entire planet in a single frame, wrapped in a thin layer of atmosphere so delicate it looks like it could tear. But there were other impacts, less visible, equally important. The technology developed for space exploration didn't stay in space. Satellites, initially launched to study weather and map terrain, became essential infrastructure. Communication satellites made global television and internet possible. GPS satellites, originally designed for military navigation, became so ubiquitous that billions of people now depend on them every day without thinking about it. Medical technology advanced because of space research. Devices for monitoring astronauts' health in orbit led to better portable medical equipment on Earth. Water purification systems developed for spacecraft now provide clean drinking water in remote areas. Insulation materials, flame-resistant fabrics, even the technology behind modern camera phones, all of it has roots in space exploration. These weren't intentional. No one went to the moon to invent better water filters. But the process of solving the extreme challenges of space, of keeping people alive in an environment where everything wants to kill you, forced innovation, and that innovation spread. There's an economic argument here too. For every dollar spent on space exploration, studies suggest several dollars of economic return flow back into society through technological spin-offs, job creation, and scientific advancement. But the argument isn't really about money. It's about what happens when you push the boundaries of what's possible. when you demand solutions to problems that have never been solved before. The tools you create, the knowledge you gain, it doesn't disappear. It spreads. It improves lives in ways that weren't predicted. But there's a darker side to the impact as well. The same rocket technology that sent humans to the moon also created intercontinental ballistic missiles. The same engineering that builds satellites builds weapons. The history of space exploration is inseparable from the history of military development, and that's a tension we still haven't fully resolved. The Cold War drove the space race. National pride, competition, the desire to prove ideological superiority, all of it funneled enormous resources into rocket development. Without that geopolitical pressure, it's unclear whether we would have reached the moon as quickly as we did. Maybe not at all. And after the Cold War ended, funding dropped. Public interest waned. The Apollo program was cancelled. Plans for Mars missions were shelved. The focus shifted to more practical concerns, more immediate problems. Space exploration became less about reaching farther and more about maintaining what we'd already achieved. The shuttle program, the space station, satellites. Important work, essential work, but not the kind of bold, impossible-seeming leap that captured imaginations the way Apollo had. That shift had consequences. The generation grew up without the same sense of possibility, the same belief that humans could do the impossible if they tried hard enough. The dream of space faded into the background, replaced by other priorities, other crises, other futures. But the impact didn't disappear. It just changed form. In recent years, private companies have started pushing into space. SpaceX, Blue Origin, others. They're building reusable rockets, lowering launch costs, planning missions to Mars and beyond. The motivation isn't purely national pride anymore. It's commerce. It's ambition. It's the belief that space offers resources, opportunities, futures that Earth alone can't provide. Whether that's true remains to be seen. But the shift from government-led to private-led space exploration represents a new kind of impact, a new way of thinking about who space belongs to and why we should go there. There are ethical questions embedded in this shift. Who owns space? Who gets to exploit its resources? If we find life, even microbial life, on another world, do we have the right to disturb it, to colonize, to change it? These aren't abstract philosophical debates. They're real questions that will need real answers in the coming decades. And the impacts of those answers, whatever they turn out to be, will echo through history just as powerfully as the first footprints on the moon. But perhaps the most profound impact isn't technological or political or economic, it's psychological. The knowledge that we can leave changes us. Even if most people never go to space, the fact that humans have touched another world, that machines we built are still travelling through the darkness billions of kilometres away, that we've looked back at Earth and seen it whole, that knowledge shifts something deep in the collective consciousness. We're no longer purely earthbound. We're a species that reached beyond our cradle. And even if we don't go much farther for a while, even if the next great leap takes decades or centuries, we've proven it's possible. We've crossed a threshold that can't be uncrossed. That's the real impact. Not the technology, not the science, but the awareness, the understanding that we're part of something larger, that the universe isn't somewhere else. It's here. It's us. We've only just begun to explore it. The echoes of space exploration will continue for generations. Some we can predict, most we can't. But they'll be there, rippling outward, shaping how we think, how we build, how we understand ourselves and our place in the cosmos. That's what happens when you reach for the impossible. The reach itself changes everything, whether you grasp it or not. Space exploration has always been driven by two opposing forces. On one side, the dreamers, the people who look up at the stars and feel an irresistible pull, a deep, irrational conviction that we belong out there. On the other side, the skeptics, the people who look at the same stars and see only distance, danger, and 1,000 more pressing problems right here on Earth. Both are right, and both are necessary. The dreamers built the rockets. They calculated the trajectories. They volunteered to strap themselves into capsules and ride, controlled explosions into the unknown. Without dreamers, we'd still be earthbound, staring upward, wondering. But the skeptics kept the dreamers honest. They asked hard questions. They demanded evidence. They forced every design to be tested, every calculation to be checked, every risk to be weighed. Without skeptics, the dreamers would have launched too soon, failed too often, lost too many lives. The tension between them is what makes exploration possible. Wernher von Braun was a dreamer, the German rocket engineer who designed the V-2 missile during World War II and later became one of the chief architects of the American space program. He dreamed of Mars long before anyone thought seriously about reaching the moon. He sketched out plans for space stations, interplanetary ships, permanent colonies on other worlds. His vision was grand, almost absurdly optimistic. But he was also practical. He understood that dreams needed engineering, that ambition needed funding, that to reach Mars, you first had to convince people to fund a trip to the moon, and to do that, you had to tie your dream to something immediate, something concrete. Competition with the Soviet Union. Pride. Von Braun's legacy is complicated. His rockets helped win the space race, but they were built on knowledge gained from weapons designed to kill. The V-2 was responsible for thousands of deaths during the war, and the labour used to build them came, in part, from concentration camps. The dream and the horror are inseparable. That's the uncomfortable truth of space exploration. It didn't begin in innocence, it began in war. On the other side, there were skeptics like Dwight Eisenhower, the president who initially resisted the idea of a moon mission. He thought it was too expensive, too risky, too much like a stunt. He preferred smaller, incremental steps. Robotic probes, scientific satellites, practical applications. But after the Soviet Union launched Sputnik, after the political pressure mounted, Eisenhower relented, not because he stopped being a skeptic, but because he recognized that sometimes dreams are necessary, that sometimes you need a goal that seems impossible just to unite people, to inspire them, to make them believe they can do more than they thought. John F. Kennedy was a different kind of dreamer. He didn't care much about space itself. He cared about perception, about leadership, about showing the world that America could achieve things the Soviet Union couldn't. When he gave his famous speech in 1962, declaring that America would go to the moon before the end of the decade, it wasn't because he loved science. It was because he understood the power of ambition. And it worked. The Apollo program became a national project, a shared goal that transcended politics. Engineers, scientists, technicians, factory workers, all of them united by the idea that they were part of something historic. The skeptics were still there, still questioning costs and risks and priorities, but the momentum was unstoppable. Then there are the astronauts themselves, the ones who actually went, people like Neil Armstrong, who stepped onto the moon's surface and became the most famous explorer in history. But Armstrong didn't think of himself as a hero. He thought of himself as an engineer, someone doing a job, solving problems, following procedures. The dream was secondary to the work. Buzz Aldrin, who walked beside him, was more openly ambitious. He wanted the recognition, the place in history, but he also understood the responsibility, the weight of representing not just a country but an entire species. The first humans to walk on another world, that's a burden as much as an achievement. And then there were the people who never went but made it possible. The engineers at NASA, the mathematicians, many of them women, who calculated trajectories by hand before computers could do it reliably. Katherine Johnson, Dorothy Vaughan, Mary Jackson. Their names weren't famous for decades, but without them, the missions wouldn't have succeeded. That's the human element. Not just the people in the spotlight, but everyone behind them. The dreamers and the skeptics, the visible and the invisible, all working together, arguing, compromising, pushing forward. But not everyone agreed it was worth it. There were protests. Critics who said the money spent on space should go to education, healthcare, poverty reduction. They asked, rightly, why we were spending billions to put footprints on the moon when people were starving on Earth. The answer wasn't simple. Some said space exploration inspired technological progress that helped everyone. Some said it was about survival, about ensuring humanity didn't keep all its eggs in one planetary basket. Some said it was about the intangible value of exploration itself, the idea that humans need goals beyond survival, dreams beyond comfort. But the critics weren't wrong. The costs were real. The trade-offs were real. And the question of whether space exploration is worth it remains unresolved. It's a question each generation has to answer for itself. Today, the dreamers are still dreaming. Elon Musk talks about colonizing Mars, about making humanity a multiplanetary species. Jeff Bezos talks about moving heavy industry off Earth, preserving the planet by building infrastructure in space. They're billionaires, not government scientists. Their motivations are different, their methods are different, but the dream is recognizable. It's the same one that drove von Braun and Kennedy and Armstrong. The belief that we belong out there, and the skeptics are still skeptical. They point out the technical challenges, the biological risks, the ethical questions. They ask whether we should focus on fixing Earth before trying to leave it. They remind us that space is vast, cold, and indifferent, that the universe doesn't care whether we survive or not. Both sides are necessary. The dreamers keep us reaching, the skeptics keep us grounded, and somewhere in the tension between them, progress happens. Slowly, messily, imperfectly. But it happens. The human element isn't neat. It's not a straightforward story of heroes and villains. It's complicated, contradictory, full of compromise and conflict. But it's also what makes exploration possible, because humans are the only species we know of that looks at the impossible and tries to do it anyway. Not because it's easy, not because it's practical, but because something deep inside us, something irrational and undeniable, says we should. That's the element that defines how far we can travel, not the technology, not the physics, but the willingness to keep trying, even when the odds are against us, even when the skeptics are right, even when the dream seems absurd, because sometimes the absurd becomes real. And when it does, it changes everything. Somewhere in the process of reaching for the stars, something shifted. Not all at once, not with a single revelation, but gradually, like dawn spreading across a landscape, humanity began to see itself differently. We are, right now, living in the first era in which humans can leave their home planet, not easily, not casually, but genuinely, physically, actually leave. That fact, simple as it sounds, represents a fundamental change in what it means to be human. For millions of years, our ancestors lived entirely on the surface of one world. They couldn't conceive of anywhere else. The sky was infinite and unreachable. The stars were lights, nothing more. The idea of travelling to them, of standing on the moon, of sending machines to other planets, it would have seemed like magic, like myth, like something reserved for gods, not mortals. But now we've done it, and that changes the story we tell ourselves about who we are. The awakening isn't about achieving a specific distance or reaching a particular destination. It's about the shift in awareness that comes from realizing we're no longer bound by the same limits that constrained every previous generation. We're no longer a purely terrestrial species. We're something new, something that exists on the threshold between worlds. That threshold is uncomfortable. We're not yet a true spacefaring civilization. We can't live independently beyond Earth. We can't sustain ourselves on other planets. We can't travel between stars. But we're no longer entirely earthbound either. We exist in the liminal space between what we were and what we might become. And that liminality, that in-between state, is where the awakening lives. One of the most profound realizations is how unified Earth looks from space. Astronauts describe it again and again. The borders disappear. The conflicts seem small. The planet becomes a single entity, fragile and whole, floating in darkness. That perspective doesn't solve political problems. It doesn't erase disagreements or end wars, but it shifts something. It makes it harder to see other nations, other peoples, as fundamentally separate, because from space there's only one world, and we all live on it together. The overview effect, as it's called, isn't just an emotional reaction. It's a form of awareness, a recognition that the divisions we maintain, the walls we build, the us versus them narratives we cling to, they're choices. Not facts, not inevitabilities, choices, and choices can be changed. There's another awakening too, quieter but equally important. The realization that we're part of something much larger than ourselves. Not in a religious or mystical sense, in a literal, physical sense. The atoms that make up your body were formed in the cores of stars. The iron in your blood, the calcium in your bones, the carbon in your DNA, all of it was created billions of years ago, in fusion reactions so powerful they eventually tore those stars apart. When they exploded, they scattered their contents across space. Those contents drifted through the Rund of Mora galaxy, coalescing into clouds, then planets, then life. You are, quite literally, made of stardust. That's not poetry, it's chemistry, it's physics. It's the observable, verifiable history of matter itself. And that means you've already travelled farther than any spacecraft ever will. The elements that became you have crossed light years. They've moved through explosions, collisions, gravitational wells. They've been recycled through countless forms before finding their way into the structure of your body. In that sense, asking how far we can travel misses the point. We're already travellers. We've always been travellers. The journey didn't start when we built rockets. It started with the first stars, the first atoms, the first stirrings of matter organising itself into complexity. Space exploration, then, isn't about leaving. It's about returning, about tracing the path of our origins back through the cosmos, about understanding where we came from and what we're part of. That's the awakening, the realization that the distance between us and the stars isn't as great as it seems, not because we've figured out how to cross it quickly, but because we're already connected, already intertwined with the same processes that create galaxies, ignite suns, and scatter life-giving elements across the void. This awareness doesn't answer all the questions. It doesn't tell us how to build faster rockets or survive longer journeys. But it shifts the question itself. Instead of asking how far we can physically travel, we start asking how far our awareness can reach, how deeply we can understand, how connected we can feel to the universe around us. And those questions have different answers, because awareness doesn't require fuel. It doesn't face the tyranny of the rocket equation. It can expand as far as imagination and knowledge allow. We can see galaxies billions of light years away through telescopes. We can detect the faint whispers of the Big Bang in the cosmic microwave, background radiation. We can map the structure of the universe, trace the formation of stars, predict the eventual heat death of everything, all of it without leaving Earth. That's a kind of travel too, not physical, but real nonetheless. The mind reaching outward, connecting with distant realities, understanding things that exist far beyond the reach of our bodies. And maybe that's enough. Maybe the goal isn't to physically visit every star. Maybe it's to understand them, to know them, to recognize that they're part of the same story we're part of. There's a humility in this awakening, a recognition that we're small, that our lives are brief, that the universe is vast and mostly indifferent to our existence. But there's also a strange kind of pride, because we're the part of the universe that can notice itself, that can ask questions, that can look outward and inward simultaneously and recognize the connection between the two. Stars don't know they're stars. Galaxies don't contemplate their own existence, but you do. You can look up at the night sky and understand that you're seeing ancient light, photons that travelled for years or centuries or millennia before entering your eyes. You can hold that contradiction in your mind, the vastness and the intimacy, the distance and the connection. That capacity, that awareness, is what defines how far we can truly travel, not the distance our bodies cover, but the reach of our understanding, the depth of our curiosity, the willingness to keep looking, keep asking, keep wondering, even when the answers are impossibly far away. The awakening is ongoing. It didn't happen all at once with the first rocket launch. It's happening right now, in this moment, as you think about these ideas, as you consider your place in the cosmos, as you realize that the question of how far we can travel isn't just about spacecraft and fuel. It's about consciousness, about awareness, about the strange, beautiful fact that the universe, through us, has found a way to know itself. And that might be the farthest anyone can travel, not to the edge of space, but to the edge of understanding. And from there, to look back and see everything, all of it, all at once, connected and whole. Here's the truth we've been circling, the one that sits beneath all the calculations and missions and dreams. The question of how far we can travel in space isn't really about distance at all. It's about belonging. Every spacecraft we launch, every mission we plan, every rocket we fire into the sky, it's an attempt to answer a deeper question. Not how far can we go, but where do we fit? Are we meant to stay on Earth forever, or are we meant to spread outward, to become something larger than a single planet species? The physics gives us one answer. The cold, hard mathematics says we're limited, that the stars are too far, that our bodies are too fragile, that the timescales involved are longer than civilizations, longer than species, longer than the forms of life we recognize. But something else inside us gives a different answer. something irrational and undeniable that says we should try anyway. That the universe didn't give us consciousness and curiosity just to keep us trapped on one small world. That the fact we can ask the question means we're meant to seek the answer. Both answers are true, and both are incomplete. The deepest truth is this: we're already travelling, right now, every second, not just in the sense that Earth is moving through space, though that's true, but in the sense that existence itself is a journey, from simplicity to complexity, from matter to awareness, from atoms to life to consciousness to whatever comes next. Space exploration is just one expression of that journey, one way of continuing the motion that's been ongoing since the first particles cooled after the Big Bang, one way of participating in the universe's slow, patient process of organizing itself into ever more complex forms. And that process doesn't care about our timelines. It doesn't care if it takes us 100 years or 100,000 years to reach the nearest star. It doesn't care if we ever physically leave the solar system. What matters is that we're part of the process, that we're contributing to it, that we're pushing, in our small way, toward greater understanding, greater reach, greater connection. That's the revelation. The journey isn't about reaching a destination. It's about the movement itself, the effort, the attempt, the willingness to look outward and say, we want to know more. We want to go farther. We want to understand what's out there. And every time we do that, every time we launch a probe or send a signal or build a telescope, we're succeeding. Not because we've arrived somewhere, but because we're still moving, still trying, still part of the ongoing story of matter learning to know itself. There's a paradox here. The more we explore, the more we realize how little we know. The more we discover, the more questions emerge. It never ends. It's not supposed to end. The exploration itself is the point. When Voyager 1 crossed into interstellar space, it didn't find answers. It found more questions. What's the boundary of the heliosphere really like? How does the solar wind interact with the interstellar medium? What does space look like between the stars? And when we eventually answer those questions, new ones will appear. That's how understanding works. It's not a destination. It's a direction. A motion towards something that keeps receding, not because we're failing, but because the universe is larger than any single answer. So how far can we travel right now? In physical terms, we've covered it. Low Earth orbit, the moon. That's where we are. That's what current technology allows. In physical terms, we've won times, but in terms of awareness, we've travelled much farther. We've mapped the cosmic microwave background, the afterglow of the Big Bang itself. We've detected gravitational waves from colliding black holes billions of light years away. We've seen galaxies so distant their light has been travelling toward us since before the sun existed. We've travelled, through instruments and mathematics, to the edge of the observable universe. We've looked back in time nearly 14 billion years. We've seen the structure of reality itself, the way space curves, the way time dilts, the way matter and energy are interchangeable. That's a journey. One that happens in the mind, in the models, in the understanding. But it's real. It changes what we know. It changes who we are. And maybe that's the deepest truth. That the real journey isn't measured in kilometers or light years. It's measured in understanding, in the expansion of consciousness, in the slow, difficult process of becoming aware of what we're part of. Physical travel will come someday. Maybe not in our lifetimes, maybe not for generations, but it will come because the motion is already underway. The process is already in action. We're already part of the story of the universe reaching outward, trying to understand itself. And that process, once started, doesn't stop. It might slow, it might pause, it might take detours, but it doesn't stop. Because curiosity, once awakened, doesn't fade. It compounds. Each generation builds on what the previous one learned. Each discovery opens new paths. Each question leads to more questions. That's the revelation. We're not separate from space. We're not visitors from somewhere else trying to explore a foreign place. We're part of it. We're expressions of the same physical laws that govern galaxies and stars. We're made of the same materials. We're driven by the same fundamental forces. When we reach outward, we're not leaving home. We're exploring another room in the same vast house we've always lived in. When we ask how far we can travel, we're really asking how much of ourselves we can discover, how far our awareness can extend, how deeply we can connect with the reality we're embedded in. And the answer to that question isn't fixed. It's not limited by fuel or propulsion or biology. It's limited only by willingness, by curiosity, by the choice to keep looking, keep asking, keep trying, even when the distances seem impossible. That's how far we can travel, as far as we choose to, as far as our awareness can reach, as far as our understanding can extend, and that distance, unlike physical space, has no theoretical limit. It can grow forever. It can encompass everything. It can connect us to the farthest reaches of reality and the deepest truths of existence. Because in the end, distance is an illusion, a convenient fiction we use to organize space. But awareness doesn't have distance. Understanding doesn't have limits. Connection doesn't require proximity. You are, right now, connected to everything, to the stars that formed your atoms, to the galaxy that holds our sun, to the universe itself, vast and ancient and ongoing. That connection isn't metaphorical, it's literal, it's physical. It's the deepest truth of what it means to exist. And if that's true, then the question of how far we can travel has already been answered. We've travelled as far as the universe extends, because we're not separate from it. We never were. We're part of the journey itself, and the journey has no end. Pause here for a moment. Let the silence settle. Let your breathing slow. We've travelled through history, through physics, through dreams and limitations and revelations. We've looked at the numbers, the missions, the machines that carry our curiosity outward. We've seen how far we've gone and how impossibly far everything else remains. Now, in this quiet space, ask yourself, what does it all mean? Not in a grand philosophical sense, not in terms of destiny or purpose, but personally, intimately. What does it mean to you that we live in an era when humans can leave Earth? That spacecraft are crossing the solar system right now? That footprints exist on the moon, untouched for more than 50 years, waiting in dust that will preserve them for millions more? What does it mean to know that you're made of star matter? That the calcium in your bones was forged in a supernova? That the oxygen you're breathing right now was created in the core of a star that died before our sun was born? These aren't rhetorical questions. They're invitations. Invitations to sit with the strangeness of existence, to recognize how improbable it all is, how delicate, how brief. You are alive at a specific moment in cosmic history, a moment when humanity has just barely learned to reach beyond its cradle, but hasn't yet figured out how to go much farther. A moment of transition, of possibility, of uncertainty about what comes next. 1,000 years ago, no one could have imagined this. The idea that humans would walk on other worlds, that machines would travel for decades through the void, that we'd map the structure of the entire observable universe. It would have seemed like myth, like impossibility. 1,000 years from now, assuming we survive, what we've accomplished will probably seem quaint, limited. The first awkward steps of a species that didn't yet understand what it was capable of. But right now, in this exact moment, we exist at the threshold. Neither fully earthbound, nor truly spacefaring. Aware of the vastness, but still confined to a tiny corner of it. Dreaming of the stars, but struggling to reach the nearest planets. That threshold is uncomfortable, but it's also precious. Because it's where transformation happens. Where one thing ends, and another begins. Where the impossible slowly, awkwardly, painfully becomes possible. Think about the astronauts who've been to space. Not many. Only about 600 people total, out of the 100 billion humans who've ever lived. A fraction so small it barely registers. And yet, those 600 carried something back with them. A perspective. An awareness. A shift in understanding that spread outward through their words, their photographs, their presence. That's one way travel changes things, not through mass migration, not through widespread access, but through the few who go and return transformed, carrying new ways of seeing that ripple outward to everyone else. Maybe that's enough. Maybe we don't all need to go to space. Maybe it's sufficient that some do, that they see what needs to be seen, that they bring back the perspective we all need, the reminder that Earth is rare, that life is fragile, that the universe is vast and indifferent, and somehow, against all odds, we're here to notice it. But there's another kind of travel too, the kind that doesn't require leaving the ground, the kind that happens when you look up at the night sky and really see it, not as decoration, not as background, but as a map, a history, a reminder of where you came from and what you're part of. Every star you see is a sun. Most of them have planets. Some of those planets might have life. Some might have consciousness. Some might be looking back at us right now, asking the same questions we're asking. How far can we travel? Are we alone? What does it all mean? We don't know the answers. We might never know. But the questions themselves are a form of connection, a reaching out across the void, an acknowledgement that distance, vast as it is, doesn't erase the possibility of kinship, of shared experience, of other minds, other awarenesses, scattered through the cosmos, all wondering the same things. That's humbling, and it's beautiful, because it means loneliness might not be permanent, isolation might not be inevitable. The universe is vast, yes, but it's also full of potential, full of possibility, full of mysteries we haven't even begun to unravel. So what does it mean that we can travel in space, but not very far? What does it mean that we've walked on the moon but struggle to imagine reaching Mars? What does it mean that the stars remain, for now, beyond our grasp? It means we're human, limited and reaching, fragile and persistent, bound by physics but driven by something that doesn't care about limits, something irrational, something beautiful. It means the journey is just beginning, that we're in the earliest chapters of a story that will unfold over millennia, that whatever we accomplish in our lifetimes will be a small part of something much larger. And that's okay. It's more than okay. It's the nature of exploration itself. No single person discovers everything. No single generation solves all the problems. The work is cumulative. Each step builds on the previous one. Each generation hands the baton forward, a little farther along the path, a little closer to understanding. And when you think about it that way, the question of how far we can travel right now becomes less important. What matters is that we're travelling at all, that we're moving, that we're trying, that we're part of the ongoing story of consciousness reaching outward, asking questions, seeking answers, refusing to accept that anything is truly impossible. That's the meaning. Not in a single achievement, not in a specific distance, but in the motion itself, the effort, the curiosity, the stubborn, beautiful refusal to stop wondering. You're part of that right now. By listening to these words, by thinking about these questions, by looking up at the night sky and feeling that pull, that quiet longing to know more, to go farther, to understand what's out there. That pull is ancient. It's been with us since the first humans looked up and wondered, and it will be with us as long as consciousness endures. It's not going away. It's not fading. It's just waiting, patiently, quietly, for the next generation to take the next step, and the next, and the next. How far can we travel in space right now? As far as our bodies allow, but the real journey, the one that matters, isn't measured in distance. It's measured in understanding, in awareness, in the slow, steady expansion of what we know and what we care about. And that journey has no limit. It can go as far as curiosity can reach, as far as consciousness can extend, as far as the universe itself, which, when you think about it, is infinitely far, because the universe doesn't have an edge, it doesn't have a boundary, it just keeps going. And so do we, not in our bodies, not in our lifetimes, but in the questions we pass forward, the dreams we share, the understanding we build together, generation after generation, reaching always towards something we can barely imagine but somehow know is there, waiting, patient, infinite. That's the meaning. And it's enough, more than enough, it's everything. The story of space exploration doesn't end. It accumulates. Every mission, every discovery, every person who looks up and wonders, they all add to something larger. A legacy that grows with each generation, that shapes how we see ourselves and what we believe we're capable of. That legacy isn't just in the hardware. It's not just the rovers still operating on Mars or the space station circling overhead or the Voyager probes drifting through interstellar space. It's in the shift that happened when we first left Earth and realized what that meant. A shift in consciousness, a change in identity. Before 1961, we were earthbound. After, we were something else, something new, a species that had touched the void and come back to tell about it. That change is permanent, even if we never go any farther. Even if we stopped launching rockets tomorrow and abandoned every plan for Mars and the Moon and beyond, the fact that we left, that we proved it could be done, that knowledge can't be unlearned, the threshold is crossed. We're no longer a terrestrial species dreaming of space. We're a spacefaring species learning to navigate it. That's the legacy. And it lives on in ways both obvious and subtle. The obvious ones are technological. Communication satellites that make global connection possible. GPS systems that guide us through cities and wildernesses, weather satellites that warn us of storms, Earth observation satellites that track climate change, deforestation, urban growth. All of it depends on our ability to reach orbit and maintain presence there. All of it is infrastructure now, so integrated into daily life that most people don't even think about it. But the subtle legacies run deeper. There's the inspiration, the children who watch rocket launches and decide to become engineers, the students who study physics because they want to understand how spacecraft navigate, the artists who create work inspired by images of Earth from space, the writers who imagine futures where humanity has spread across the solar system, across the galaxy, becoming something larger than it is now. That inspiration doesn't always translate directly into space exploration. Sometimes it leads elsewhere. Medicine, technology, art. But it all comes from the same source. The belief that impossible things can become possible, that limits can be pushed, that we don't have to accept the boundaries we're born into. That belief, quiet as it is, shapes culture. It changes what people think they can achieve. And that matters more than any single rocket launch. There's also the knowledge, the pure scientific understanding gained from space exploration. We know more about the solar system now than we did 50 years ago. We've mapped Venus's surface. We've watched storms rage on Jupiter. We've seen the rings of Saturn up close. We've landed on Titan, a moon with liquid methane lakes and a thick atmosphere. We've discovered ice on the moon, water on Mars, organic molecules on comets. Each discovery changes our understanding of how planets form, how life might emerge, how common or rare our existence might be. And that knowledge doesn't stay confined to scientists. It spreads. It becomes part of the story we tell ourselves about the universe and our place in it. There's the perspective too. The overview effect. The realization that Earth is a single system, fragile and interconnected. That perspective has influenced environmental policy, international cooperation, the way people think about borders and nations and belonging. It's hard to quantify. You can't point to a single policy or movement and say, this happened because of space exploration. But the shift is there, visible in the rise of global environmental awareness, in the images used to advocate for planetary protection, in the language of interconnection and shared responsibility. The legacy isn't just what we've done, it's what we've become, a species that's tasted the infinite and can't forget the flavour, that's looked back at its home from a distance and understood, viscerally, how rare and precious it is. That understanding will outlast the rockets, it will outlast the missions, it will outlast individuals, governments, even civilizations, because it's encoded now, not just in records and photographs, but in consciousness itself, in the collective awareness of what we are and where we come from. And that encoding is a form of immortality, not for individuals, but for the knowledge, the perspective, the awareness. It gets passed forward, generation to generation, each one adding to it, refining it, carrying it farther. The astronauts who walked on the moon are aging now. Soon, they'll all be gone. But what they saw, what they felt, what they brought back, that doesn't disappear. It lives on in the people they told, in the records they left, in the shift they helped create. The same will be true for the next generation, and the one after that. Each will add their piece. Each will push a little farther. Each will carry the legacy forward, not because they have to, but because they want to. Because once you're part of the story, you can't help but continue it. Right now, there are missions in progress. The James Webb Space Telescope, peering deeper into the universe than any instrument before it, seeing galaxies that formed when the cosmos was young, Perseverance still roaming Mars, collecting samples that might one day return to Earth. Artemis preparing to send humans back to the moon for the first time in more than 50 years. These aren't endings, they're middles. Chapters in a story that's still being written. Each one will add to the legacy. Each one will shift, in some small way, what we know and what we believe is possible. And beyond the official missions, there are the private efforts. Companies building reusable rockets, lowering the cost of access to space. Entrepreneurs dreaming of asteroid mining. Lunar bases, Mars colonies. Some of it will succeed, some will fail. But all of it is part of the same legacy, the same motion forward. Because the story of space exploration isn't really about destinations. It's about the journey, the ongoing, cumulative, never-finished process of reaching outward. And that process, once started, doesn't stop. It just keeps going, slowly, patiently, across generations, across centuries. One day, probably long after everyone alive today is gone, humans will stand on Mars. They'll look back at Earth, a pale blue dot in the sky, and feel the same thing the Apollo astronauts felt. The fragility, the connection, the awareness of how far they've come and how far they still have to go. And they'll be part of the legacy too. Part of the same story that started with the first human who looked up and wondered. Part of the same motion that carried us from caves to cities to orbit to the moon to Mars to wherever comes next. That's how the story lives on, not through any single person or achievement, but through the continuation itself. The refusal to stop, the quiet, persistent determination to keep reaching, keep wondering, keep moving forward. You're part of that legacy, right now, by being curious, by listening, by caring about the questions even if you'll never see all the answers. That's enough. That's how it spreads. That's how it endures. The legacy isn't in the past. It's in the future, in what comes next, in what we choose to carry forward. And that choice, quiet as it is, shapes everything. It determines not just how far we travel, but who we become in the process. And that's a legacy worth protecting, worth building, worth passing on. Some lessons don't belong to a single generation. They echo forward and backward through time, touching everyone who's willing to listen. The lesson of space exploration is one of those. It's not about rockets or planets or technology. It's about something deeper, something that connects the first humans who looked up at the stars with the ones who might someday live among them. The lesson is this: you are already travelling, not metaphorically, literally. Right now, as you rest wherever you are, you're moving through space faster than any spacecraft humanity has ever built. Earth rotates at about 1,600 kilometers per hour at the equator. You're spinning with it, though you don't feel it. Earth orbits the Sun at about 107,000 kilometers per hour. You're carried along, circling the center of the solar system once a year, traveling nearly 1 billion kilometers without ever leaving your chair. The Sun itself moves through the galaxy at about 720,000 kilometers per hour, dragging the entire solar system with it. You're part of that motion too, circling the galactic center once every 230 million years. And the galaxy itself is moving, drifting through space, part of a local group of galaxies, all of them dancing around each other, all of them moving through the expanding fabric of the universe. Add it all together, and you're traveling at millions of kilometers per hour. Every second, every breath. You've never been still. You never will be. Motion is the default state of existence. Stillness is an illusion. That's the first echo. The realization that travel isn't something you choose, it's something you are. You're a moving pattern of atoms and energy, temporarily stable, briefly conscious, forever in motion. The second echo is connection. Every particle in your body has a history, a journey. The hydrogen in your cells was formed in the first few minutes after the Big Bang. The heavier elements were forged in the cores of stars that lived and died billions of years ago. The carbon, nitrogen, oxygen, iron, calcium, all of it travelled across light years before finding its way into your body. You are, in the most literal sense, made of the cosmos. You're not separate from it. You're not a visitor observing from the outside. You're an expression of it. A temporary arrangement of matter that learned to think, to wonder, to look back at the universe and recognize itself. That connection is permanent. It doesn't matter how far you physically travel. You're already part of the journey, already woven into the fabric of space-time, already travelling with the flow of matter and energy that's been ongoing since the beginning. The third echo is awareness. Of all the matter in the universe, most of it drifts unconsciously. Stars burn without knowing they burn. Planets orbit without wondering why. Galaxies collide without awareness of the collision. But you're different. You notice. You wonder. You ask questions. You're the part of the universe that's developed the capacity to know itself. And that capacity, rare and precious as it is, matters. It matters because awareness changes things. A star that burns for 1 billion years affects its surroundings through gravity and radiation. But consciousness affects things through choice, through intention, through the ability to act not just according to physical law but according to meaning. You can look at the night sky and decide that distance doesn't erase connection. You can learn about the universe and choose to care about what you learn. You can reach, even symbolically, toward the stars, and that reaching, however small, contributes to the ongoing story of consciousness expanding through the cosmos. That's the timeless lesson, not that we should travel farther or faster, but that we should recognize what we already are. Travelers, cosmic matter temporarily organized into awareness, part of a journey that began long before us and will continue long after. And that recognition changes everything. It turns the question of how far we can travel from a technical problem into an existential meditation. Because if you're already traveling, if you're already connected, if you're already part of the cosmos, then the limits don't matter as much. The distance becomes less important than the awareness of it. Think about the light you see when you look at the stars. That light left its source years ago, decades ago, centuries ago. Some of it has been travelling since before humans existed, before Earth existed, before the sun formed. And it arrives here, now, entering your eyes, carrying information across impossible distances. That's a form of travel. A connection that doesn't require physical proximity. A way of touching something distant without ever leaving home. That's what telescopes do. They let us travel backward in time. See things as they were, not as they are. The farther we look, the deeper into history we go. The most distant objects we can see existed when the universe was young, when the first stars were forming, when everything was closer together and simpler and just beginning. Looking outward is looking backward, and that means every observation is a kind of time travel. A way of reaching across billions of years to witness what was. That's the fourth echo. Time and space are woven together. Distance is also duration, and the farther we reach, the deeper we see. not just into space, but into time, into the history of everything. The timeless lesson isn't about achieving a specific goal. It's about participating in the ongoing story, about recognizing that you're part of something vast and ancient and still unfolding, about understanding that the journey doesn't end with your life or your generation or your species. It continues, always, because motion is fundamental, change is inevitable, and consciousness, once it appears, has a tendency to persist, to ask questions, to seek understanding, to reach toward the unknown even when the reaching seems futile. That persistence is the lesson, not that we will definitely reach the stars, but that we'll keep trying, that each generation will push a little farther, that the motion, once started, sustains itself through curiosity and wonder and the refusal to accept that anything is truly impossible. You carry that lesson with you, not because you chose to, but because you're part of the pattern, part of the ongoing wave of consciousness moving through the cosmos, part of the universe waking up to itself, slowly, imperfectly, but unstoppably. And that's the echo beyond time, the lesson that doesn't belong to any single moment, the understanding that transcends generations, the truth that remains constant even as everything else changes. You are traveling, you are connected, you are aware, and that's enough. That's everything. That's the lesson the universe has been teaching since the beginning. And you, right now, by listening, by thinking, by wondering, are proving that the lesson has been learned. The echo continues. Through you, through everyone who comes after, through the endless motion of matter and energy, organizing itself into ever more complex forms, through the slow, patient unfolding of awareness across the cosmos. And that echo, quiet as it is the answer to every question about distance and destination. Because the journey isn't somewhere else. It's here. It's now. It's you. And it always has been. And so we arrive back where we began. Here. Now. This moment. This breath. This quiet space between sleep and waking, where questions soften and understanding settles. The question was simple. How far can we travel in space right now? The answer, we've learned, is both smaller and larger than it first appeared. Smaller because the physical limits are real. The moon is as far as humans have gone. Mars is years away. The stars remain, for now, beyond reach. The universe is vast, and we are small, and the gap between our ambitions and our capabilities is measured in light years and lifetimes. But the answer is also larger, because travel isn't just about distance, it's about awareness, understanding, connection. And in those terms, we've already travelled farther than any physical journey could take us. We've reached back to the beginning of time. We've mapped the structure of the cosmos. We've learned that we're made of star matter, that we're part of an ongoing story that began billions of years ago and will continue long after we're gone. That knowledge changes everything. It turns isolation into connection. It turns limitation into possibility. It turns the question of how far we can go into a meditation on what it means to be here at all. Tonight, as you drift towards sleep, imagine yourself floating, not in a spacecraft, not in orbit, but in the quiet space between thoughts, where distance loses meaning, where time slows to a gentle pulse, where the universe, vast as it is, feels intimate and close. You're not separate from the stars, you're made of them. You're not outside the cosmos looking in. You're part of it, looking at itself. And that perspective, that awareness, is the farthest anyone can travel. because it connects you to everything, to the beginning and the ending and all the moments in between. The machines we've built will keep travelling. Voyager will drift for millennia, carrying its golden record, a message from humanity to whoever might find it in the distant future. The space station will continue circling, a human presence maintained continuously in the void. New missions will launch, new discoveries will be made, new distances will be crossed. But those are just the outward signs of something deeper. The motion that really matters isn't in the machines, it's in the consciousness that builds them, the curiosity that drives them, the awareness that sees meaning in the journey itself, not just the destination. You carry that awareness. You are, in this moment, the leading edge of the universe's exploration of itself. The questions you ask, the wonder you feel, the quiet recognition of your connection to everything, that's the real journey, and it's ongoing. It doesn't end with this episode or this thought or this lifetime. It continues, through you and through everyone who comes after, through the endless motion of matter organizing itself into consciousness, through the slow, patient process of the cosmos waking up to what it is. And in that process, distance becomes irrelevant, because awareness doesn't need to travel. It just needs to expand, to deepen, to recognize more and more of what's already there. So when you ask how far we can travel, the answer is, as far as awareness reaches, and awareness, once awakened, has no limit. It can encompass the observable universe. It can touch the edge of time itself. It can connect the smallest atom to the largest galaxy, the briefest moment to the eternal pattern, the individual consciousness to the cosmic whole. That's where we are, right now, at the threshold, between what we were and what we're becoming, between Earth and the stars, between limitation and possibility, between the question and the answer that keeps unfolding, moment by moment, across the infinite canvas of existence. The stars will be there tomorrow, and the next day, and for billions of years to come. They're patient, they don't hurry, they don't demand, they just shine, constant and quiet, offering their light across the darkness. And you're here, receiving that light, part of the same pattern, part of the same story, part of the journey that has no beginning and no end, only the endless present moment where everything unfolds. How far can we travel? As far as this moment, as deep as this awareness, as wide as this connection. And that, in the end, is infinitely far, because infinity isn't a distance, it's a direction. And the direction is always here, always now, always the quiet recognition that you're part of something vast and beautiful and ongoing. Rest now. Let the questions settle. Let the wonder remain, soft and present, like starlight through a window. You don't need to solve the mysteries of distance and time and space tonight. You just need to know that you're part of them, that you belong to the cosmos as surely as it belongs to you. And that belonging, that connection, that simple, profound truth is the answer to every question about how far we can travel. We're already there. We always have been. We just needed to notice. The journey continues, but for now, rest. The stars will wait. The universe will keep expanding. And you, here, now, in this perfect moment of stillness and awareness, you're exactly where you need to be. Welcome home. Welcome to the quiet side of the cosmos. Welcome to the infinite journey that begins and ends right here, in this breath, in this thought, in this awareness that connects everything to everything else. The stars are shining, the universe is moving, and you are part of it all. Rest well, the night is long, and the cosmos, patient as always, will still be here when you wake.